We will continue with Alpine fault line data analysis. We estimate liquefaction susceptibility at each asset. So first asset we choose is bridge, and the second asset is buildings. So in this lab, we will estimate liquefaction susceptibility at each bridge. Hint 1. Given this has come from a global data set, it won't always intersect nicely with the high-resolution New Zealand coastline we are used to. For those bridges that don't intersect the raster, assign a liquefaction susceptibility based on the nearest existing bridge with a value. Hint 2. If you split your data frame into different parts, you can always merge two or more geodata frames back together at the end using the pandas function. Concat and output data frame equal gpt.geodataFrame open bracket pandas.concat open bracket open square bracket. We'll put the two data frames, data frame 1 comma data frame 2, close the square bracket, comma ignore index equal true. So we show the calculations. So the bridges geometry, they are point geometries, and the TIF path is the name of the liquefaction susceptibility file. So we read TIF path data and show properties. So TIF plot looks like this. From raster stats, we import point query. So we will use the point query to find the liquefaction susceptibility at each near to each bridge. So from raster stats, we import point query. Bridges geometry. So from bridges geometry, let's look at one of the rows. This is just a sample that I'm just showing the calculation over here, and that prints the row number 200, and that's the point geometry. Now we use point query to find the liquefaction susceptibility at each bridge. So point query open bracket, so that geometry and bridges geometry for row number 200, that is square bracket 200 colon 201 and close the square bracket, comma TIF path, that is the name of the liquefaction file, no data equals 0, interpolate equal nearest. So we use point query to find the liquefaction susceptibility at each bridge. So list of susceptibility equal empty array, that's shown by the empty pair of square bracket. For bridge geometry in a bridges data frame and the geometric column of it, LQ underscore sus equal point underscore query open bracket bridge underscore geometry comma TIF underscore path, that's the name of the file, comma no data equals 0, comma interpolate equal nearest, close the bracket, and inside the pair of square bracket we put 0. And list of this why we put 0 is because when we find the point query, it will be printed in so if we don't put 0 in the square bracket, then it prints that. So there is a square bracket around the values. So if we put 0 inside the square bracket, then we print the values 4.0. So that's why we have this 0 inside the pair of a square bracket. List of susceptibility dot append of bracket LQ underscore source. Bridges bracket the column name LQ underscore source equal list of susceptibility. Then we sample 10 rows from the bridges data frame, and we see that we got LQ underscore source column here with the values. Then we split into known and unknown data. Here we'll assume we need to replace LQ source equals 0 as well. So known data contains all the uh, rows, all the data rows where LQ source value is not NA, and also it is more than 0. An unknown data frame contains all those uh, data rows from bridges data frame where it is not applicable is NA, or the LQ source column is equal to 0, and we display known and unknown column here, unknown data frame, the first few lines. So we see that known data frame contains LQ underscore source where the values are greater than 0 and is not NA, and unknown data frame contains LQ underscore source column where the values are not applicable and equal to 0. And then we import earnings, and we do earnings dot simple filter open bracket ignore close bracket, because when we use this s index nearest, this command over here will produce the error like assigning error. So it will say that dot location, we need to put dot location, exact location. So we don't want that error. So that's why we do earnings dot simple filter open bracket ignore close bracket. Then we find nearest known geometry of unknown geometry. So known we already know. So known dot s index dot nearest in bracket unknown geometry. So from the unknown data frame, the geometry, we will find the nearest value to the geometries of known data frame. Return all equal false, and 1, by putting this 1 over here inside this square bracket, we are there will be 2 arrays formed. So first array will contain the row names of unknown rows, and the second yeah, so the first array is for the known, all the rows that it goes through from the known data frame, and the second array will contain the nearest geometry. If it has found the nearest geometry in known geometries, then that row name will be in the second array. So that's why we put square bracket 1. So checking the first few lines of unknown data frame, we get this. So nearest underscore known underscore IDX, we get this row names. And checking the unique values of this nearest known IDX column, we get these values. Now we drop column not needed. So we from the in the unknown data frame, we don't need the LQ underscore source column any longer. So we drop this, and then we insert the LQ underscore source column from the known data frame for each of these row names in the nearest known IDX column. So this command will drop the LQ underscore source column unknown dot drop open bracket columns equal LQ underscore sus comma in place equal true, and we print the fetched view lines by passing the command unknown dot hide open and close bracket. So we get this. So now LQ underscore sus column is gone. Then in the known data frame there is LQ underscore sus column. Let's check for this nearest index, some of this index over here. Let's check what we get for, yeah, so yeah, so first we show calculation of uh, first we show the calculation. So unknown dot reset underscore index drop equal true will reset this index to from 0 to 1. So first we want to reset the index. Okay. Now let's look at the from the known data frame dot I log. Now our index location, now bracket we will put say 62. So what does that give? That gives row name 71, and for that the liquefaction susceptibility value is 3. So if this row name is uh, in the index column, uh, nearest known index column, then the LQ susceptibility we want it to be 3. So that's what we're doing by passing this command over here, joining unknown to create a LQ underscore sus column of known LQ underscore sus. So unknown equal to unknown dot reset underscore index bracket drop equal true. So we don't want another index column, the old index to be put as a new column. So that's why we say drop equal true. Dot join open bracket known. So this is the known data frame, and from that we choose LQ underscore sus. By putting the double bracket, this it changes that uh, array that's to pandas series form, pandas data frame form. And then we do dot reset underscore index, and we do drop equal true. So for that data frame that we created from this LQ underscore sus, we reset the index so that it starts from 0 and it increases, and we drop the old index by doing drop equal true, comma on equal nearest known IDX, and we check head of it. So we run this first. Okay. So after running, we see that LQ underscore sus column is created and the values are this. So for the LQ sus equal to 100, say LQ sus equal to 5, the sorry, nearest known IDX equal to 5, LQ sus in this was, let's see, 5 is the, no, that's not the name, say 4, name is 4, say 6. Noun, let's check. So for I in range, length of noun, we want noun I location, I name equal to 5. So we are checking for 5 here. Okay, we are checking for 5. So equal to 5. So let's print that data row from known data frame. We'll say print, otherwise it won't print anything. Okay, so let's insert one cell above, and we want known I location. We want to print I, so that's 0. So known I location 0. Let's print that, and let's print the row name. So we do name dot name, and that's 0. Yeah, so name is also 0, name, and oh yes, so we need to put if over here. If noun equal to 5, then print noun I log I. Print I. Okay, so the first one should give us the row name equal 5 if now name equal 5, then print I. Nothing. Let's do another row cell. Let's print I 656. I name equal 5, then print. Yeah, nothing. What about 325? Print I location. No, actually we want 5. Yeah, let's look at known data frame, and LQ sus is 3. So that's what we expect over here. And for 325, with 325 here, and LQ sus is 3. Okay. Okay, so we already ran that, and we print. Yeah, it gives us error because I clicked on run the cell twice. So I'll just insert another row above, and I'll show you. This will print the first few lines. Look at this. Drop the columns not needed in unknown data frame, unknown dot drop, and bracket, square bracket, and we want to drop nearest known IDX, comma, x is equal 1, comma, in place equal true. So this will drop the nearest known IDX, and printing the head of the known data frame. So we get LQ underscore source. Now we display known and unknown. So we get where LQ source is known and LQ source is not known. So now we show the calculation. So what we're doing is that we are concatenating the known and unknown data frame, and we ignoring the index. So it will have the known data frame, and then from the and then it will join the unknown rows, and we convert that to geodata frame by doing gpd.geodata frame. Okay, so here we are assigning that geodata frame to bridges, and then we do bridges.reset underscore index, and we drop the old index by doing drop equal true, otherwise there will be a old index column created. So we'll pass that command. So what it does is that yeah, so we can see that the noun columns, the noun rows are joined to the unrows over here, unknown rows over here. So check the unique values of LQ source. So bridges bracket LQ underscore source dot unique. So we get 43125 and not applicable. And let's visualize LQ source. So visualize LQ underscore source for bridges. Background underscore map equals South Island dot plot, open bracket, color equal light gray, close bracket. Bridges dot plot, open bracket, IX equal background underscore map, comma, column equal LQ underscore source, comma, legend equal true. and we get this map of here. And the yellow dots mean that the LQ sus value is very high, which is 5. So there is one dot here. And the very dark blue means the LQ sus value is 1. And the greenish is between 3.5 to 4.5.